What I'd like to talk about now is relativistic dynamics, or essentially Newton's laws. So up to this point, we've talked about momentum, energy, kinematics, but now let's try and incorporate what we know about Newton's laws. So Newton's first law is not a problem because I said special relativity, their postulate is that the physics is the same in these inertial frames of reference. So essentially, there's no acceleration. You're in an inertial frame. The physics is the same. So in that case, this is not a problem. We've essentially already worked out those kind of cases. Now let's consider Newton's second law, which is now kind of going to be a problem because we now deal with forces, which is the change in the momentum with respect to time. And this implies there can be an acceleration involved, which is not what we had in our postulate. So now we're dealing with what you would consider non-inertial frames of reference. And so what we're kind of do is we're not going to do the full-blown analysis because anything that involves an acceleration really should be considered by general relativity. Instead, we're just going to kind of see how can we rewrite forces in terms of special relativity. And so the starting point would be if we consider the work as the integral of the force times the length, and we can put in our change in momentum with respect to time, like so. And now what we do is I want to replace the lengths with time. So to do that, I'm going to rewrite the dl as a dl dot dt, where I'm now integrating over time as opposed to length. If I write it like that, dl dt is a velocity. So what I have is my force times my velocity, and now integrating over the time. Okay. Written like that, I can now write the velocity and the momentum relativistically. So this term becomes mu over mu. So let's write the momentum relativistically. This is mu gamma, so square root of 1 minus u squared over c squared, dotted into my velocity. So I'm treating now the velocities relativistically. So essentially what this becomes is, if you work out the chain rule, gamma m du dt dotted into u, so that's the first part of the chain rule. Now we have to take the derivative of the denominator, and so what we get is m minus 1/2 u over 1 minus u over c quantity squared to the 3/2 power dotted into u. And then we still have to work out, so let me make some room. Dotted into u, and then we have to take the derivative inside the parentheses. So I get minus 2u over c, and then I get a du dt right there. Okay, so let's clean that up. And in the end, what we should get is m times 1 minus u over c quantity squared, du dt dotted into u, plus m u over c squared, u dotted into u, du dt, all of that divided by 1 minus u over c squared to the 3/2 power. So basically I just looked for the common denominator and made one big fraction out of it. So that's what happened to the gamma over here. Okay, so now if I try and clean this up, what I should get is, well, m times u dot du dt divided by 1 minus u over c quantity squared to the 3/2 power. So essentially when you multiply through by the m here, and then you get a cancellation where essentially u dot u is u squared. So anyway, when you work it out, you get this result, which I can then rewrite as derivative with respect to time of mc squared over the square root of 1 minus u over c quantity squared. So you basically kind of reverse the chain rule, and what you get is this. Now that is d dt gamma mc squared, which is the total energy. So what we found was that that force dotted into the velocity turns out to be the change in energy with respect to time, which shouldn't really surprise you at all, because that's essentially the power. So the change in energy with respect to time is the force times the velocity, so we get the power. So the work then becomes the integral dE dt dt, which is the integral of the work, or the final energy minus the initial energy. So work is the change in the total amount of energy. And if essentially energy is conserved, that energy, internal energy, has to be conserved, or if there are external forces, the change in the energy is equal to the work. So if we treat the the momentum relativistically and the velocity relativistically, we end up with the same result that we would if we just considered non-relativistic momentum and velocities. Okay, Newton's third law is a little bit trickier. And so in the end, what I'm going to do is essentially skip it. Because Newton's third law implies a collision between one object and another object in order for the force of one object to cause a reaction force in the second object. And if I have two objects, that implies two frames of reference, and so that's getting a little more complicated than we want to deal with in this class. Okay, so what we could do is to consider the writing out the forces now in ordinary time. So if we consider, say, a force in frame bar, so the S bar frame in the y direction is the change in the momentum in that frame with respect to time, then in the unbarred frame, I would get something that looks like this. So that dt bar right here is equal to what you get in the denominator over there. I can then rewrite this as the change in momentum with respect to time, gamma 1 minus beta over c dx dt, which then looks like the force in the y direction is gamma times 1 minus beta u, the velocity in the x component of the velocity, divided by c. So I can write basically in ordinary time what the conversion of the forces would be between one frame and the other frame. Okay. If I look at the z component, what I would get is something very similar. Essentially, the force in the z component divided by gamma 1 minus beta uxc. Okay. The interesting thing is now if we look in the x component of the force, then I would get the change in momentum of x with respect to time. Don't forget the bar on the time. And that would give me now gamma dpx minus gamma beta dp0, the time component of the momentum, gamma dt minus gamma beta c dx. And if I rewrite that, then I would get dpx dt minus beta dp0 dt over gamma 1 minus beta over c times dx dt, or what you would get is the force in the x direction minus beta c dE dt, because that's what the time component of the momentum is, divided by gamma 1 minus beta ux over c. Okay. Which then I can rewrite as the dE dt as the momentum, or basically the force, dotted into the velocity, or I get the force dotted into the velocity, which now tells me that the x component of the force is the x component in the other frame minus beta over c, essentially the power over here, divided by gamma 1 minus beta ux over c. So the interesting thing is that what you have in the y and the z component is that the x velocity is now contributing to the force in the y and the z components, and in the x direction, the x force in one frame is related to the x force in the other frame, and the power that you would have there. So if you were to rewrite this, we could write in proper time a force, which now we're going to call k, with an index mu, where mu goes from 0, 1, 2, 3, and it's the proper momentum divided by the proper time, often called the Minkowski force. And if I take a look at this now, what I see is that this force in the 3 momentum, x, y, and z, would be the time conversion, the force in the ordinary time, or gamma times the force in ordinary time. And so in the end, what you get is a proper force, or Minkowski force, which is related to the force in ordinary time in gamma. So in this case, it's when you have 1, 2, or 3. And then K0 is dP0 d tau, which is 1 over c times the power, or ordinary, or proper power.